Welcome to another video about compiler construction. In a previous video, we have learned that compiler is a program that translates code written in one language to another. Usually, the input code, which we call the source code, is a higher level language code, and the output of a compiler, the target code, is the assembly code. To that end, the compilation process has been divided into 7 different phases. Each phase completes a compilation task, and then the output of the current phase becomes input to the next phase. In this video, I will provide the overview of all of those phases. So we have 7 phases. First phase is lexical analyzer. Then we have syntax analyzer, semantic analyzer, then we have intermediate code generation, then we have machine independent code optimizer, then we have target code generator, and finally we have machine dependent code generator. And then we will have our target language code. So now let's start discussing each of those phases one by one. In order to explain things clearly, I will use this simple example of, say, C code, and will show that how this code is processed by all those phases of compilation. For each phase, I will first describe its input and output. Then I will write that how to write specification of that phase, and finally what kind of errors are generated by that phase. So let's start with our first phase, lexical analyzer. Lexical analyzer phase is also known as scanning phase. So the input of our lexical analyzer phase is stream of characters. So the input is a source language code, but in form of stream of characters. Our output of the lexical analyzer phase is stream of tokens. So the first question that we should ask, what we meant by tokens. Initially, these are English language characters, and compiler has to make sense of them. So firstly, compiler read that stream and convert set of characters into lexemes. Lexemes are the smallest meaningful unit that compiler can understand. So in this case, sum is a lexeme, equal to sign is a lexeme, opening parenthesis is a lexeme, I is a lexeme, plus is a lexeme, j is a lexeme, closing parenthesis is a lexeme, multiplication sign is lexeme, and 10 is a lexeme. So these all are lexeme which compiler can understand as a something meaningful. Then compiler convert each lexeme in a form of token. Token is a tuple whose first field is token name. The second field is optional, which is attribute value. The attribute value is usually indexed to the symbol table entry. Symbol table is a data structure used by all the phases of compilation. They can store information in the symbol table, they can update information in the symbol table, and they can extract information from the symbol table. As in this example, we have 8 different lexemes, so we will have 8 different tokens. Our first token will be ID, 1. where ID stands for identifier because sum is an identifier and 1 is an index to the symbol table entry. In the symbol table, at index 1, we will have name and other information stored about this identifier sum. So we will have here name and other information stored in the symbol table at index 1. The next token will be equal to sign, and in this case we don't have to store any information in the symbol table, so our attribute value will be null. The next token will be opening parenthesis, then we will have id, 2, so at index 2 we will have I store and other information. Then we will have plus as token, then we will have id, 3 as token, where at index 3 we will have j store and its other information. Then we will have closing parenthesis as token, then we will have multiplication sign as token, and then we will have 10 as token. Note that the lexical analyzer phase also remove all the spaces, tabs, and return sign, etc. So lexical analyzer phase removes spaces also, because spaces are meaningless for the compilation phase. We just need these tokens for continuing. Now there are two questions need to be answered. Number 1, how to write specification of lexical analyzer phase. To that end, we use regular expressions. We'll do detailed videos about this phase, exploring different examples and writing different regular expressions. Then you should ask what kind of errors are produced in this phase. So in this phase, the errors produced has to do only with individual lexemes. In this phase, we don't worry about the relationship between lexemes, we only worry about the individual lexemes. For instance, in C language, we are not allowed that an identifier name starts with literal. So if I have an identifier name 87 kill, then this is an illegal identifier name in C language. So if I use such a string for an identifier name, then in this phase we will get an error which might be that illegal identifier name. So now we can update this diagram because we know that the input to the lexical analyzer phase is streams of characters, which is basically of the source language code, and the output of the lexical analyzer phase is stream of tokens. Let me clear the board and then we will continue with our second phase. Our second phase is syntax analyzer phase. We already know what will be the input of this phase because the input of this phase is the output of the previous phase, which is streams of tokens. The output of syntax analyzer phase is syntax tree, which is a compressed form of parse tree. We will learn about syntax tree and parse tree in detail. For this video, we only have to know that syntax tree is a tree whose interior nodes are operators and whose leaves are operands. So for this example, the syntax tree will be that we will have equal to sign here, and here we will have id, 1 as our node. Here we will have multiplication sign as our node, and here we will have plus sign as our node, and then here we will have id, 2, and then here we will have id, 3, and finally here we will have 10. So this is our syntax tree. Now the next question is how to write specification of this phase. We can use context-free grammar to write specification of this phase. And what kind of errors are produced by this phase? There are lots of errors regarding syntax of the language that are produced in this phase. For instance, if I have incorrect use of parentheses, then we will get this error in this phase. Similarly, if I have incorrect use of keywords, then we will produce errors in this phase. For example, if I have a for loop, but instead of specifying the for loop correctly in C language, I use this syntax, then this will be an error because I must place semicolons here. Those semicolons are not optional. I can't skip those. Even if this for loop has to run for infinite amount of time, then I must basically have here semicolons. So if I have no semicolons here, then this is basically a syntax error. Similarly, any other syntax related error must be produced in this phase. Now let's clear this board and continue with the semantic analyzer phase. So our previous phase was syntax analyzer phase, whose input was streams of tokens and whose output is syntax tree. And the syntax tree becomes the input of semantic analyzer phase, whose output is also a syntax tree, but that syntax tree has more information in it. Also, the semantic analyzer phase update the symbol table by adding more information in it. So, semantic analyzer phase input is syntax tree and its output is also syntax tree, but it has more information in it. How to write specification of this phase? Once again, we have to use context-free grammar. But the context-free grammar here has more information as compared to the syntax analyzer phase. What kind of errors we produce here? We produce type related errors. We produce maybe scope related errors. For example, if I have integer I is equal to 3.5, then as far as the syntax is concerned, this is the valid syntax. I'm assigning identifier or value. However, this is a mismatch type error because integer cannot take a float value. So we will get maybe illegal assignment error. Now, the parse tree will be updated with extra information. We can add type and scope information in the parse tree, or we can update the symbol table. Assume that my sum is float, my I is float, my j is float, but this 10 is an integer. So when we have an integer here, then either we have to produce illegal type error because this should be float also, or C compiler can automatically convert this 10 into float. To that end, it will update the syntax table by replacing this node with another node where it will say call integer to float function here, and then apply that function on 10. So that's the output of our syntax tree. Now let's continue with our intermediate code generation phase. Our next phase is intermediate code generator phase. The input of this phase is annotated syntax tree, which is a syntax tree with extra information added by the semantic analyzer phase. The output of this phase is intermediate code, which is platform and language independent code. Usually our intermediate code is in 3 address form. So we have here intermediate code generator phase, and our input of this phase is annotated syntax tree, and our output is intermediate code, which is usually in 3 address code form. We use here syntax directed definition and syntax directed translations to write specifications. So we use here syntax directed definitions and syntax directed translations to write specification. Basically, syntax directed definition and syntax directed translations are context-free grammar with some code and some rules attached with the grammar symbols or with protections. Usually this phase don't produce many errors because we have produced all the errors in the lexical analyzer phase, which are about tokens. We have produced all the syntax errors in the syntax analyzer phase, and then all the semantic errors that we can produce in the semantic analyzer phase. So usually we don't have any errors here. Now let's write 3 address code for our example. We have a temporary variable t1 and we store the result of this operation in this variable. So we will have here, let's say id2 plus id3. Then we will do this operation. So we say t2 equals to int to float 10, and then we will do this operation. So we say t3 equals to t1 times t2, and finally we store our result in id1. So id1 equals to t3. So this is our 3 address code intermediate representation. The advantage of producing this 3 address code and this intermediate representation is that we can now do lots of optimization which are machine independent. So our next phase is machine independent optimization. The input to machine independent code optimizer is 3 address code. So let's write 3 address code here, which was the output of intermediate code generation. And the output is also 3 address code, but that code is much more optimized. So output is also intermediate code, usually in the form of 3 address code, but much more optimized. So this one is optimized. So input to our machine independent optimizer phase is 3 address code and its output is optimized 3 address code. Usually we don't write specification of this phase. Instead we use lots of different algorithms here. For example, we might use dead code removal algorithm, we will use constant folding algorithm, we will use common sub-expression elimination algorithm. So there are different algorithms used in this phase. We generate no errors in this phase. Although this phase is an optional phase, however, usually all compilers have this phase with lots of code in it because this phase is very important. This phase can make your code run faster, take less RAM, less space, which is a good attribute of a compiler. Now let's optimize this code quickly. So after optimization, our code could be like t1 equals to id2 plus id3 and id1 equals to t1 times 10.0. So we have already converted it into float. We don't have to use this integer to float function. We have removed many temporary variables and now our optimized code has only 2 lines as compared to the original code which has 4 lines. So this code will run faster and will take less RAM as compared to this code. And we will learn lots of optimizations algorithms in our future videos. Finally, we have target code generation phase, which also use syntax tree translation and syntax tree definitions. And afterwards, we have here assembly code most of the time. So let's write here assembly code. And finally, we might be able to use some machine dependent optimization so that we are now optimizing our assembly code. So these are machine dependent optimization. So here we will have at the end optimized assembly code. But this phase is also optional as compared to this phase. This phase is usually much thinner because we will be able to do most of our optimization in machine independent code optimization phase. So this video has only an introduction of different phases. We will have multiple videos explaining each phase in detail. Stay tuned.